Good afternoon. Good evening. First, I want to start with the demonstration that I dropped the ball on twice last week. These are my window holders, my curtain holders. You wrap them around, and then they come back and hold it in place. And I like this demonstration because it reminds you about that attractive and repulsive force between different ends of a magnet. So, for the camera first, these are like ends of a magnet, and you might be able to tell because I'm able to hold them apart while trying to force them together. I'm physically feeling them repel each other. And I want you guys to think about two molecules doing that. Maybe not the same molecule, but maybe they are. Maybe they're two ammonium ions, NH4+, and they're sitting right next to each other, refusing to get any closer, trying to get further away. And then I want you to flip it around. I want you to try and hold the opposite ends of the magnet apart from each other and realize that it's a similar force you feel, but in reverse, forcing them together. So pass them around, play with those magnets, and remember, what you are experiencing right now is very similar to what molecules are feeling all the time. A little bit of attraction here, a little bit of repulsion there, back and forth, and then to just totally varying extents. Oh, I'm so sorry. Oh, that wasn't yours?
No, I just
Good.
would've
Then
got it.
I am less sorry then.
Cooper?
Now, to warm us up, after our discussion last week on all things general, I want you guys to try and tell me what we've got going on up there.
That's an elimination.
Good. Good.
Oh.
Compound or molecule? Both. This is a molecule, and it also has more than one type of atom, so it's also a compound. Organic or inorganic?
Organic.
Organic. How about this? Compound or molecule? Your compound might be the best fit here because it's an ionic compound. We know that because we have a metal, sodium, and a non-metal, and that's the nitrogen with the hydrogens. Sodium, when it's bonded to other things, will be ionic. So you might say it's also a bit of a molecule because we have an ionic molecule, the NH2 minus, but I don't know. This is where the lines get a little bit blurred. Organic or inorganic?
Inorganic.
Nothing organic about it?
Nothing organic.
Why not? No carbons in that NaNH2 structure. Good. Product here will create a triple bond. Organic or inorganic?
Organic.
Organic. And our byproduct here, NaBr, inorganic ion, inorganic salt. We also get another byproduct. I forgot about that. We get two equivalences of this. Organic or inorganic? Inorganic. Good. From time to time, especially on active, where you will see most of your homework, you will see it say, ignore inorganic byproducts. That's because we're studying the organic chemistry, so we're focused predominantly on what is going on with the organic molecules. help me remember where we left off at the end of Thursday's class. Good. So we were distinguishing between sigma bonds and pi bonds, yeah? We had already distinguished between covalent and ionic bonds. So actually, I think I want to take a step back and remember something critical about the difference between covalent and ionic. Sodium methoxide, methanol. Which of them is drawn correctly? Sodium methoxide or methanol?
Methanol.
Can you tell me why? Sodium is what? Good. Sodium is charged. Sodium makes ionic bonds, which means we cannot display sodium methoxide with that Lewis dot structure line between it. What would be a better way of showing this?
Negative, positive.
Na plus
Positive,
and OCH3 minus. So how do I go from something like NaOCH3 to Na plus OCH3 minus? You don't. They're the same. That is equivalent to each other. But I can go from something like H bonded to OCH3 and also not show the bond. So this idea of having two elements written next to each other, indicates that they're bonded to each other, but it is your job to know the nature of that bond. Is it an ionic bond because of having a metal and a nonmetal, or is it a covalent bond because you have two nonmetals?
Is that true for when it's a solid and dissolved in solution?
Yes. So a lot of you have worked in medicine. You've worked with saline before, which is mostly sodium chloride solution, right? So we can indicate that it is separated, it's not crystalline, by saying its state is AQ. But you wouldn't necessarily need to say that. If you said this is a saline bag, I know that there's sodium chloride in there. I know that it's dissolved. I know that its chemical formula is NaCl, but that it's operating as Na plus Cl minus. Now, in organic chemistry, oftentimes in our reaction that we're displaying, we're assuming it already is dissolved. And we don't have to show the ions separating in dissolution. In fact, we won't show the ions separating because I want you to think about this is this. But here they're held together strongly, maybe crystalline, right? And then after, they're just pulled apart from each other once they're dissolved. It's a good question. But if you're working with a salt and you need to show it, especially, say, in a mechanism, you can just show it separated. There's no arrow pushing you can do to show them separating. You just show them dissociated. I know that can be challenging, but throughout the semester, hopefully we'll be able to apply it and make it make sense.
Ionic compounds have to be dissolved in order to separate?
Ionic compounds can be melted, at which point, as an ionic liquid, they're moving past each other, but they're still strongly interacting. Or they can be turned into gases. The northern lights that you see are gaseous ions releasing energies as they relax.
But if you have a solution that they can't dissolve in, but they're in, could some other reagent just pull it off?
One more time?
If you have a solution that the ionic compound could not dissolve in, could another reagent just pull one of the ions out of the compound without it dissolving?
No, not easily, because a lot of those ions are buried within the crystalline structure. So you would need to first excavate from the surfaces of the crystal and then get into the insides, which is much harder to do if you're not also pulling away the other ion. So, no, I don't think you can pull out one ion selectively without dissolving the whole thing. Good question. Okay, back to our conversation about bonds. Our covalent bonds predominantly made up of pi and sigma bonds. So I gave you guys this perspective that when you have two overlapping orbitals, here I've got s orbitals, but we can do the same thing with overlapping p orbitals or overlapping hybridized orbitals. What you're going to see looks just like a sphere. And that spherical orbital is what we call the s orbital. So by alliteration, we call it a sigma bond. And it's always these head-on overlaps that give us our sigma bonds. When you get a side-on overlap, which only happens with p orbitals, it doesn't happen with s orbitals, and you put yourself into the plane of it, it projects as if it's just a p orbital. So by alliteration, we call it a pi bond. We're not going to learn this, but metals can pi bond with each other using d orbitals. Again, just a side-to-side overlap, that which, looking through the internuclear axis, looks like a p orbital. But metals can also take those d orbitals and put them face to face and have 4 regions of overlap, which, looking through the internuclear axis, looks like a d orbital, so it's called a delta bond. But in organic chemistry, this is where we're limited. Now, I want to move from here into our idea of hybridization, because all of our bonds are made up of orbitals overlapping, and so it's important that we understand the orbitals at play. So first, let's review atomic orbitals. I want us to go just to the third shell. So here's the first shell, second shell, third shell, and let's review the orbitals that our periodic table predicts. Down in the first row, what's that orbital? That's our 1s orbital. This is a very common orbital in organic chemistry. Why? Because it's the only orbital hydrogen has. And there's a lot of hydrogen in organic chemistry. But to be honest, it's not that interesting. So we're not going to talk about it that much. What orbitals do we have in the second row? 2s and 3 different 2p orbitals. So I'm going to call this 2px, 2py, and 2pz. These are mathematical equations that all create the same shape, but lie along different directions. So 2px could lie in our x-plane, 2py could lie in our y-plane, and if 2pz was shown in our z-plane, it's actually eclipsing itself. So I've got a circle in front of a circle. A little challenging to draw. And those are all distinct from each other because they define orientation, which the spherical orbital, the s orbital, cannot. This isn't going to be on your test or anything, but I want you guys to understand orbitals a little bit better. Orbitals in the same shell always have the same number of nodes, but those nodes take on 2 different forms. They're either spherical nodes, meaning that they take the orbital itself and separate it into regions that are spherical, or they are angular nodes, and they take each lobe and divide it into different regions. The 1s orbital has 0 nodes. The 2s orbital has the same number of nodes as 2p, but the 2s has one spherical node. This is like a volleyball inside of a tennis ball. It's a sphere within a sphere. That's a spherical node that it has. The 2p orbitals have an angular node, one lobe distinguished from another. And the node is a region where electrons are never found. It's a region of 0 probability. And you'll notice that we separate those lobes with different shading. Does anybody remember what the shading represents? I like to call this the sign on the equation that's the math is obeying. The equations that define electrons' motion, they often begin with plus or minus, and it's got this big math equation. So maybe I'm oversimplifying it, but the way that I like to remember this is that the electron moves differently in this region than it moves in this other region. If you think of the electron moving forward in one region, then it's just moving backwards in the other. All right, after our 2s and 2p, after our second shell, what do we get? 3s. How many nodes in the 3s orbital? 2. Each shell is going to increase by one number of nodes. First shell has 0 nodes, second shell has 1 node, third shell has 2 nodes. How many of those nodes are angular? None of them. Both nodes in 3s are spherical. This is a tennis ball inside of a volleyball inside of a basketball. 3 spheres separated by spherical nodes. The 3p orbitals have how many nodes? How many nodes did 3s have? Then 3p has 2. Okay, times 3 gives us a total of 6, but each one has just 2 nodes. And because it's a p orbital, it's going to have this one angular node, but because it's in a next highest shell, it's also going to have an additional spherical node, which means the 3p orbitals look really funky, where they've got kind of this p shape, and then they've got this bigger exterior p shape. That alternates shading because it's a node, and the sign changes as you pass through a node. And then what comes after 3p? Not 5d. Same shell? 3d. These are our 5 3d orbitals. How many spherical nodes does a d orbital have here? 0 spherical nodes. How many angular nodes does a d orbital have here? 2 angular nodes. This is what differentiates types of orbitals within their shells, whether the math equation is creating spherical nodes or angular nodes. 0 nodes, 1 node, 1 spherical, 1 angular. 2 nodes, 2 spherical, 1 spherical, 1 angular, 2 angular. Now there's, we're not going to deal a lot with d orbitals, so I like to draw these. You don't have to. There's 2 main shapes that d orbitals take on. One of them is this kind of flower shape, and you can see the 2 angular nodes. They're just a straight vertical and straight horizontal line. But then the d orbitals also have this dz squared, which has a torus, a donut that goes around the middle. Now those are still angular nodes, but they are horizontal angular nodes, parabolic angular nodes, one that goes up away from the torus, one that goes down away from the torus. So all orbitals in the same shell, they have the same number of nodes. they take on those nodes differently, which create these unique shapes, unique orientations, unique energies that electrons then fill into selectively.
Is it a ring around?
Yeah, it's a donut around what kind of looks like a p orbital, but the p orbital is of the same phase.
Is it an actual ring or is it some weird shape?
It's a torus. It's a donut.
Torus, is it?
Yeah.
So does a node just mean somewhere where electrons aren't?
A node means somewhere where electrons are not. What are the electrons we're going to spend the most time with in organic chemistry? We are going to deal the most with valence orbitals. Which of these? P? Which P? 2p or 3p? Probably a lot of 2p. But to be honest, when atoms bond, they don't like these orbitals. Reason being, electrons repel. Now I told you guys that electrons are magnets. Cooper, could you pass my magnets up to me from behind you? I told you guys that electrons are magnets. Why is it that electrons like to pair? Balance? Like negative and negative balances each other? It's a bit confusing, right? When an electron spins, that spinning of a charged particle creates a magnetic field. I think my north and south might be wrong, I apologize. So that electron becomes a little magnet, and now if an electron spins the opposite way, I get an opposing magnetic field, and now my two little magnets are balanced by pairing with each other. Maybe this is too simplified, but it gets the job done for us to explain why these like charged particles repel each other most of the time, but actually prefer to be in pairs. Now, once they're in pairs, those pairs repel each other. So, if you're going to pack electrons into an atom, those electrons want to repel as much as possible. Atoms that are made like in the core of a star and then shot out, they're often not bonding with anything. So their electrons just go into this generic pattern, this lowest energy state. But once everything starts bonding, these orientations create tons of repulsion. For instance, 2 electrons in each of the p orbitals, all of those electrons are 90 degrees from each other, and that creates a lot of repulsion, and they want to push each other away. Not to mention 2 electrons in an s orbital, which has basically infinite repulsion with each of the p orbitals. So this can't possibly be the lowest energy state. It's just the beginning state. So we're going to deal a lot with the s and p orbitals, predominantly the 2s, 2p orbitals. So let's get into hybridization.
In order for 2 radicals to bond, do they have to be already spinning opposite directions, or is there one goes up next to it, the other one stops, spins the other way?
Great question. I have never heard the answer to that. Maybe. The question was when radicals pair and come together to create a covalent bond, do they need to be in opposing spins already, or will one of them reverse its spin? And really, electron spin is hard to explain. So it's possible that you have enough energy, they'll find their way to a bond. Okay. I'm trying to emphasize here that the reason behind hybridization, which is going to be a very core part of our class, the reason for hybridization is energy stabilization. Hybridization is taking math equation A and summing it with math equation B to get math equation C. Or maybe we could say math equation A plus B. So regions where A and B overlap with each other and both start with positive, inflates. They sum together. And regions where A and B overlap but have opposing signs, they deflate. They compress. They cancel each other out. So we get constructive interference and destructive interference. Maybe the math equation idea slips away from you here. So if you've ever worked with, if you've ever made waves in a pool, this is trying to cancel out waves that are coming towards you by creating an opposite wave that eats up that energy, or trying to make giant waves by summing a wave that's already existing with another one. This is what we're dealing with. So let's look at the combinations that are common. First, let's talk about sp hybridization. By the way, there is no hybridization that doesn't utilize the s orbital. You'll notice that the s orbital has the most repulsion with all of them. So if you're going to minimize repulsion, get rid of that spherical orbital. We are taking a sphere and we're overlapping it with this lobed propeller. And because of that oddity of plus minus, we're actually going to get two things out of this. Two orbitals in, two orbitals out. Now, just based on orientation, which of my p orbitals have I worked with here? 2px. So how many axes will my new orbitals have access to? Just one. I've only hybridized the x p orbital, which means the new orbitals will only lie on the x-axis. So I get an orbital that looks like this, and an orbital that looks like this. Notice that they still have two lobes like a p orbital, but one of them is big like an s orbital. That's the summation effect. And I get both of them. Now I've drawn them separately because it's easier to understand what the shape is that you're seeing, but they actually overlap some amount of space. They share the same nucleus at that node. But if I draw it this way, it looks a lot more confusing, right? Like cartoon eyes that are crossing. You can't really see what is one orbital, what is the other, when they are drawn accurately overlapping at the node. And the most important takeaway here is that these orbitals align linearly from each other. So this creates the potential for two sigma bonds with linear geometry. One sigma bond from each hybridized orbital. Additionally, this can have two pi bonds. Because it still has an unhybridized PZ and PY. And those pi bonds are perpendicular to each other. Other question?
Do the electrons, how close do the electrons get to the nucleus?
That close.
The middle there? Okay. Yeah. Is the nucleus a node?
The node runs through the nucleus, yeah.
So electrons are like two dumbbells, they're like jump.
Yeah, jump without jumping, right? It's more like a wave.
Teleport?
Sure, yeah. Or they just are that shape. Not that they need to be in one place or the other. They are that shape. I know it's odd. Let's look at some examples of organic compounds that have this sp hybridization. We've got one of them. Oh, we had one of them on the board earlier. Our alkyne carbons have two sigma bonds and two pi bonds each. So when you look at that triple bond, you can identify carbon, sigma bond, 2 pi bonds, sp hybridized. Can you guys give me some others? There's one other for sure that I'd like you guys to tell me about. Common in OChem. Something with an sp hybridized carbon atom. Carbon to hydrogen triple bond? No. Carbon to nitrogen triple bond. We call this the nitrile group or the cyano group, and we're going to spend a lot more time studying its chemistry this fall. 2 sigma bonds, 2 triple bonds. Can you tell me any other atom that has sp hybridization? Some of you would have seen this, some of you may not have seen this. This is called an allene or a cumulated diene. It's when one carbon in the center has 2 double bonds to adjacent carbons. So it's like an alkene, it's a diene that accumulate at the same carbon. These carbons on the outside, those are sp2, but this carbon on the inside is sp. Now, one last bonding scenario that you're going to see this fall. I always forget the name of this. I believe it's called the carbonium ion, but I actually like to think of it as a carbonyl cation because it often forms from a CO double bond and takes on this hybridization. Now you'll notice that oxygen there has a positive charge, and that's because oxygen takes on a positive charge when it has 3 bonds. Both atoms there are sp hybridized. All right, everybody good with this side of the board before I start erasing it? Great. I do want you guys to feel free to take pictures of the board if you want it. Every time I take a picture of something, it stays there in my camera roll forever. But you're always welcome to. Just scream at me if I'm erasing something that you need a picture of. Okay. Next set of hybridized orbitals. The sp2 orbitals. Now this happens when you take an s orbital and you sum it with 2 p orbitals. Does that not look confusing? Just wait till we get to sp3. How many orbitals should I produce by this mathematical summation? 3. I take 3 orbitals in, I should get 3 orbitals out. What axes should my orbitals have access to? X and Y. This is going to create not a line, but a plane. If I have just one axis, I have a linear geometry. If I have 2 axes, I have planar geometry. But not just that, the whole point of this is to minimize strain. So I'm not just going to have them randomly on a plane. I don't know if you guys remember, but any 3 points creates a plane. But I'm going to try and minimize their repulsion by spreading them out from each other as much as possible. What geometry would that have? It's going to look like a triangle, right? They're all going to be equally apart from each other. Now here, you'll notice that the orbitals are a little bit closer in size, but definitely still not P-shaped. And once again, I've shown them separate from each other so you can get a taste for what they really look like. But if you were to overlap them all, then you get this. They all overlap at the nucleus. How many sigma bonds can arise from this sp2 hybridized atom? 3. Each of these hybridized orbitals sets itself for being a sigma bond. 3 sigma bonds with trigonal planar geometry. How many pi bonds can an atom that is sp2 hybridized take? Just 1. Why? Good. Only p orbitals make pi bonds. There's only 1 p orbital that's left on this atom. So here's a fun thing. If you know the hybridization, you know how many p orbitals it has. Or if you know how many p orbitals it has, you know its hybridization. Let's look at some sp2 hybridized bonds in organic chemistry. Do you recall what functional groups are in this molecule? Aldehyde, which is a type of carbonyl, and alkene, the carbon-carbon double bond. So where are my sp2 hybridized atoms? Each of the 3 carbons here is sp2, and the oxygen is also sp2. By being in that double bond, the oxygen has sp2 hybridization. There's others too. By the way, you guys are going to learn how to make this molecule by reacting a precursor compound with itself. So this is a compound that you guys will synthesize by the end of the semester. This compound here has a carbon-nitrogen double bond. You'll notice the changing in bonding patterns when it's carbon to oxygen versus carbon to nitrogen. Nitrogen needs more bonds. So oxygen just has that double bond. Nitrogen has another bond to a hydrogen. Both of the atoms there are sp2 hybridized. Any others that you want to share? Now, I've only shown an aldehyde, but all of our carbonyl family exists there. Ketones, carboxylic acids, esters. All right, the last way that you can hybridize your atomic orbitals to lower energy for your atom is by sp3 hybridization. And this is where the real fun comes in when you're drawing these. You draw your px, py, and your s, but then to draw your pz, you're just drawing on top of it. You got that circle with a circle behind it. How many dimensions will these new hybridized orbitals have access to? All 3 dimensions. All 3 axes are being combined. And there is a mathematical proof that you can do. When I TA'd for inorganic chemistry in grad school, the students had to do this mathematical proof. You can do a mathematical proof that shows that a tetrahedron is the lowest energy, the largest displacement of these orbitals. I think you're just going to have to take my word for it. Now I'm going to try to draw the orientation according to this. This is the shape of a tetrahedron. if you take your fingers, you can kind of model this. Take these 3 fingers on one hand and your pointer on another. You've got 2 fingers that are in plane, and then another 2 that are in plane with each other, but one comes towards you and one goes away. That's your tetrahedron shape with the nucleus at the middle. And that's what I'm going to try to draw with my hybridized orbitals. You'll notice that this one is mostly white low because the red is hidden behind it. And this one is mostly red low because the white is hidden behind it. That's because this is coming towards you and this is going away. Challenging to draw. But this is a 3-dimensional class, so I want you to have that awareness of the 3-dimensional nature.
You just use your arm for the
Yeah, you could use your forearm, I guess, but it's not totally positioned correctly, and it changes the scale quite a bit. Okay. sp3 hybridized atoms. Oh, how many sigma bonds? 4? Or 1? Jamie? No? Hybridized orbitals will make sigma bonds. Hybridized orbitals will not make pi bonds. Since all of the orbitals have been hybridized, we'll be able to make 4 sigma bonds here with a tetrahedral geometry. But because we have hybridized all of our p orbitals, we cannot make any pi bonds. We can do a variety of different atoms that have sp3 hybridization in organic chemistry. So let's put an OH group on this carbon chain, an NH2 group, an SH group, and then let's do a bromine to represent our halogens. All right, here's the rub. I've put up here in blue all the different bonds that these hybridization states can make, but not all of the bonds need to be there for a specific hybridization. For instance, you can't have 4 bonds without being sp3 hybridized, but you can be sp3 hybridized without 4 bonds. You still are taking that hybridization to lower electron repulsion energy, but it can be repulsion from lone pairs. So all of the carbons that are here in my structure, they all have 4 bonds. Each carbon in this structure is sp3 hybridized. No double bonds shown. Can't have any p orbitals. They must all be sp3. But the oxygen only has 2 bonds. So am I suggesting that it's sp hybridized? No, because that would not minimize the repulsion that its lone pairs feel. So 4 electron regions, 1, 2 to different bonds, 3, 4 to lone pairs. This is sp3 hybridized. Similar with the SH. Similar with the NH2. 3 bonding regions, 1 lone pair. Minimize their repulsion by being sp3. And then similar with the halogen. 1 bonding region, 3 non-bonding regions, minimize their repulsion by making the atom sp3 hybridized. And the nice thing is, you don't have to do any of the work. The atoms do it for themselves. Okay.
Is diamond tetrahedral?
I always forget. Yeah, I believe diamond is a tetrahedral carbon bonding environment, which is why it's so strong.
Does it have to hybridize?
Yeah, in order to become tetrahedral, it has to hybridize. Graphene is sp2.
Why can't the lone pairs just bond with something?
Why can't the lone pairs go bond with something?
Yeah. What am I missing? That I
The carbons don't have lone pairs in diamond. They all have covalent bonds.
But
And they're
do you
bonded.
have to hybridize for two lone pairs to bond?
No, you don't have to hybridize to create a bond. But the only time atoms really aren't hybridizing, to some extent, is when they're in the core of a star or being ejected by a supernova. After that, once bonding begins, atoms are typically hybridizing their orbitals. Or really, I should say the math is changing to govern how electrons behave. Atoms aren't putting any... Well, I don't want to speak for atoms. I don't think atoms are making a conscious decision about how to hybridize. But I don't know. They could be conscious. This just might not be what they're consciously deciding. Okay. Now, I want to work with you guys on a chart. I'm going to help set you up for it. And then I'd like you and your neighbors to work together on filling it in. And please just make plenty of space for this chart. It's a really good refresher, and it's something that I would encourage you to try and build on your own without looking at your notes to see how well you can do with it. Now, along the top, we're going to have our various common elements in organic chemistry: carbon, nitrogen, oxygen, and the halogens. That's going across a row. We will see sulfur, we will see phosphorus, just not as commonly. And because sulfur and phosphorus are in the third row, they expand their octets, they do some other crazy bonding stuff. On the vertical column, what I'd like you to have is a +1 row, a neutral row, and a -1 row. Does anybody remember doing this in OCHEM 1 with me? Great. Then it should be easy for you guys to help your partners. So what I'd like you to do is make sure that you are working with someone who didn't take OCHEM 1 with me. So raise your hand if you didn't take OCHEM 1 with me. You know what? Can I make you guys move around? Would you be okay with that today? What I'd like to do is actually have you guys break into two groups who did have OCHEM 1 with me and who did not have OCHEM 1 with me, and then pair you off. Now, groups of 4 you off into groups to fill out this table. And let's do that first, and once you get settled, I'll give you an idea of what I want here. So, people who did not take OCHEM 1 with me, and people that did take OCHEM 1 with me. Lab doesn't count as
What
taking
about
with
the
me.
hybridization of us that did but don't remember this stuff?
Yeah, still with me.
Okay.
No.
Because that would mean
No, you can't.
that would mean it's not hybridized. If you have 1 sigma 3 P's, it's not.
So you might be able to find that in a supernova. All right, we've got more on this side, don't we? So I'm going to do, I think, groups of 3 and see how it spans out. So let's do Russ, Connor, Matt as a group. Can you remind me your name?
You're all good. I wasn't here. Maddie.
Maddie, thank you. We'll do Maddie, Cameron, and Jamie as a group. We'll be Luis, Christina, and Killian as a group. Jacob, Cooper, and Axel in the back as a group.
You want the chair?
Long time no. Yeah.
Courtney,
No, you get the
I'm
chair.
going to have you work with Roja and Russell over there. And this is so embarrassing. Thank you. I'm going between Kenna and Caitlin and Kate Hardy. And I'm like, I know her name is different on canvas than it is.
It is. I played you.
Kayla, I'm going to have you with Naira and James. Okay. In this chart, I want you to show me as many bonding patterns as you can that these atoms can take on that give them these charges. So I'm going to give you an example. I'm going to fill one of them in for you completely. Carbon can have a neutral bonding environment when it has 4 sigma bonds, when it has 3 sigma bonds and 1 pi, aka a double bond, when it has 2 sigma bonds and 2 pi, which can look like a triple bond on one side, single on the other, or double bonds on both sides. And carbon can also be in a neutral bonding environment when it has 3 bonds and a radical. Now, I'm just putting an example of 3 sigma bonds, but really any instance where your carbon has 3 bonds and a radical counts. So you'll notice that's all 4 bonds except for the case of the radical. So I want you guys to try and come up with as many bonding patterns as you can to fill in the rest of this square. To give you a leg up on that, I'm going to give you a mathematical equation that you can use to remind yourself of when an atom will take on a specific charge. Does anybody remember my equation? It's not my equation, the equation.
Valence electrons minus the dots plus bonds.
Good. The formal charge on your atom is equal to the number of valence electrons it has, 4, 5, 6, 7, minus the number of dots, meaning radicals or lone pairs, plus the number of bonds, meaning half the number of bonding electrons. So I want you guys to spend the next 10 to 15 minutes on this together, solving as many bonding patterns as you can. Ready? Break.
Okay, so this chart basically
Oh, you just have to chart.
first column like the already remembered it. And basically there's like a pattern, so like when the carbon has one formal charge, has one lone pair, so the pattern is basically like the next one's like neutral, has one pair.
Because
So
I have 5 valence electrons, right? And then like 3 bonds.
yeah.
Plus the 2 lone.
Christina, just so you know, you're like front and center in the video, and you're welcome to be there. I just don't know if it's gonna, if you want to be there.
Oh, I
Okay, okay. You're not blocking anything. You're not blocking anything. I'm just thinking of our friends that are watching online. Well, it's great actually. They get to watch you work out your thought process.
I guess. I'm self-conscious.
I just,
already knew it was there.
I'm sorry. Then I shouldn't have said anything. You know, if you want, I could just pause it. I should have just paused it instead of saying that to you.
I don't really care that much.
Well, there's only 3 options for the plus one, right? In it? Only 3 options for the plus one? Uh-huh.
I don't know. I didn't fill out all the different ones. I was just kind of showing him how the chart like works, like the pattern of it. So then when like the idea has a number one, you have 2 bonds, like how the opposite is at neutral.
Oh, okay. So you're. Sorry, can you read that? Again. So when the. So you're, as you move up one with the oxygen, have 1 lone pair and 3 bonds for it to be. Oh, okay. Okay, that's super easy. So you're just moving it up, and then you'll kind of take care of that. And then as we move to halogens, you remove one of the bonds, and then add another. you would move this. You would move this pattern up, right?
Yes, exactly.
Okay, that makes sense.
Plus one in the charge. Plus one in the charge?
Yes,
Positive.
correct.
Cation.
Yes.
With 8 electrons.
Sorry if I didn't make that one.
Everything has 8
no.
electrons.
Today.
What?
No, it's okay.
I could do 7?
No, that
You could do
makes
more?
sense.
Do less,
It's
yeah.
kind of nice that it's arranged that way too.
So there's a lot of
So the way
possibilities.
that I was taught was basically
So
the
many.
formula, but this is a lot easier than going through and like
Yeah.
reading everything.
I thought so too. Yeah. I use these charts so much on like every test, honestly.
Can we draw cations?
You had Dr. Ryan Holcomb, right?
You have
Yeah.
to.
Great. Awesome.
Those are cations, those are anions.
That makes total
There you
I
go.
thought he was a pretty good professor. He was just very assignment intensive, and I took it with calculus, so I was
Oh yeah.
suffering through the semester. But I think I would have liked it a lot better if I was just taking one in the course
Yeah.
instead of taking it with other courses.
Yeah. I had him for Gen Chem 1 and he was great.
Yeah, he's a really cool guy. He's really open to helping you out, and
Yeah.
looking through stuff, which is really helpful.
Yeah.
I don't want to like go so fast and like see. That's nice.
Why can't you have carbon with 4 bonds? An alkene?
You're
Probably an
Al-Majnun.
Alcone?
Carbon, like I said, you might be able to find a spot where
I don't want the crazy area. I want to know why it's not in the normal area.
it would be too high energy strength.
Why?
Think about the electron repulsion. Think about how close your nuclei have to be. It would just be crazy high energy. Not stable. The opposite of stable.
Why? Because the Z shell's in the way?
Because in order to get your nuclei close enough for the s and pz orbitals to overlap, and for the px and py orbitals to overlap,
Maybe that.
excuse me,
I mean, you need these ones that are in this plane.
you're going to have two sets
You need these
of
ones.
bonding electrons. The s and s overlap electrons, and the pz overlapping electrons.
In the same area.
They're going to be taking up the exact same physical space. So, meanwhile, the p orbitals that are creating pi bonds,
And those ones.
they're going to be relatively further away, taking up less space, less repulsion. But these orbitals that are lying directly over each other, they're going to create a ton of strain, a ton of repulsion.
Have you heard of the oval?
The oval?
In the building here?
Like messing
No, I have not.
but like keeping the
I'll keep going.
Like the charge.
Good job.
Making sure the charge stays the same.
You're saying things, and I'm like, break out our
Should we draw lone pairs?
You can draw lone pairs, yes. In fact, I would say on this, it would be best to draw lone pairs.
Would a radical halogen be positive?
No, radicals are almost never charged.
Oh, gee. What am I thinking of?
You're never going to. So what about double? What about triple? A triple bond to a halogen would actually be a plus 2 charge. Might feel weird, but. Good draw.
Actually, I have to go,
Okay.
I was gonna tell you,
First day back, and you only 6 rounds.
I can't, I have to remember my classes. I have my physics at 6 o'clock.
Oh,
So I'm kind of being late.
Whereas this one's not, right?
Being late
So
and
I'm
being
like,
early.
what's
Being
this?
late, not being late, I'll be.
Can nitrogen only make 4 bonds? Nitrogen can only make 4 bonds?
I'll be there.
Catch the recording then when you get home.
I will. Yeah.
Great.
Yeah,
I actually talked to somebody when I got your email, and I was like, I feel bad you guys didn't set them up for success. And she said, no, actually, we've had conversations with professors like you, and we actually encourage students wherever they take OPM1 to stay there for OPM2. Yeah. My goal has always been to set you up so you have a foundation to struggle better with all of those professors and work. But I guess the idea is the content is just going to flow better.
Yeah, I think so too. And different teachers from different styles. I don't want to take exams. That's a lot of.
But you should be able to.
I can take your exams. Yeah. It's just I think when you take your notes, you end up learning it. It's like a study.
Exactly, which is the goal.
Yeah. So I'll probably be leaving this class around this time.
Okay.
I think I could maybe run into issues with examples.
Oh yeah. Maybe try to be late to that class. That's one exam. It's just one midterm.
Yeah. So I think it's I think it's on Thursday. I can do this class.
Oh,
So I'll be there on time for that.
yeah. I hate to say it, but because you got the videos, try to prioritize that.
Yeah, I'll do everything I can.
Okay.
Thank you, Jim.
Take care, Jamie.
Well, I'll just document everywhere.
You got it. How we doing?
Do atoms need to bond to be neutral?
Atoms don't need to bond. Like, for instance,
Not-
the atoms that are
Nope.
thrown out of the stars. Hello. How are you?
Yeah, good. Just drawn.
Moving along.
Like, where does it go?
Okay. Oh, extra
Like,
bond.
where's it? It's neutral when it's got a double bond.
Yeah, good. Just pick another example.
I forgot.
So then I'm guessing.
Atom can be positive?
Carbon?
Yeah.
Yeah.
Lone pair.
Jacob,
No,
you,
that's negative.
I was at
using the line or did you buy
Like if it has three bonds.
And the lone pair?
Yeah.
Oh, that would be negative.
No one pair, but an empty.
Good.
So it's gone?
Yeah, so it would be like an ion. So it would be a
Paper
verbal
actually
ion.
froze off my OCD. So then I'm like,
Not the only one.
I had a lab student once. who was,
Yeah,
like,
that would be
reading
like,
a
I
letter.
feel like you'd have to have that.
He did it for one lab and he was like, that was not
So,
acceptable. Well, whatever works. That's
Yeah.
right.
You have to have that.
Seriously. How you guys doing? Yeah. Or doing things that you're usually like that. Well, you are breaking some of them. The halogens is what I'm looking at. You got a lot of bonding halogens there. Now, to be fair, some of the halogens could do it because they can expand. But they probably won't do it. So if I were to picture the ones to focus on, it would be this one. And the radical
you working? Do you work 5 or?
About
You work
house
hours?
so 3 lone pairs and 1 dot,
Okay.
1 unpaired. All of the other ones I would ignore.
Yeah.
I think technically you're right. We have all of those possible bonding patterns.
Okay. That's kind of fade away.
You're not gonna see it. That'd be like when it's bonding with I don't know, other content weird things. So I wouldn't worry about that. That one's right. Three lone pairs.
Is it like harder to get higher
All right, guys. I want to start transitioning out of this soon. So, what I'd like for your group to do is pick one bonding pattern that you liked and bring it to the board. And then also take about 5 minutes as a break to get up and stretch your legs and get your blood flowing. So in just over 5 minutes, we're going to get back into the lecture material. In that time, move around and bring something up.
Okay. Sure. So you're right up there. Which one are we? I can go right.
No problem.
Thank you.
No, just add one. Unless you want to.
These guys drive me clean. You'll check these, right?
Yes.
Should I, if I think one is wrong, should I just write what I think is right next to it?
No, I'll fix them. But you can point them out to me in a little bit.
Okay.
Unless it's one that you drew. Yeah, that would be different.
Oh.
All right, everybody. So I want to talk about some of the examples that you put up here because some are great, some work but are not realistic, and I kind of want to pull us away from looking at them since we're not going to see them throughout the semester, okay? So first of all, in our positively charged carbons, the only one I was given was carbon with a triple bond and a positive charge, no lone pairs. This is plausible, but it's really not likely. The ones that are much more likely, carbocations. Carbons with a with 3 sigma bonds and a positive charge, and carbons with a double bond and a single bond and a positive charge. These carbocations were both seen in OChem 1. This is, say, during an E1 or SN1 reaction. And this actually occurs in some reactions with alkynes, like HX additions to alkynes. Can you guys tell me the hybridizations? What is the hybridization of this carbon here? That's pretty quick. This side of the room is saying sp2. Any takers over here? Agree or disagree? Yeah? 3 bonding regions. So spp, sp2. There's no pi bond, but there is an unhybridized p orbital. It's not filled with any electrons. These other 3 regions, they want to hybridize to spread themselves out as far as possible, minimize their electron repulsion, so they pick sp2.
Trigonal planar?
Yeah, sp2 trigonal planar.
Well, then if you wanted to add a group to that, then you'd have to unhybridize all the other bonds. Wouldn't that break the bonds?
No, it would change hybridization again, but it doesn't break their bonds. It would take it from sp2 to sp3.
And without breaking it.
Without breaking it. The electrons can do weird things. What's the hybridization here? sp, which is why I drew it linear. It has 2 electron regions, even though it only has 3 bonds. All right, down on the bottom, I've got some carbanions, 3 sigma bonds and a lone pair, triple bond and a lone pair, double bond and single bond with a lone pair. And then I have this. Anybody want to own up to it? What's the issue here? Yeah, it's got more than 8 electrons. So, formal charge counts. This does work. This carbon would have a negative charge, but it doesn't exist because it creates a broken octet, which is different than this. This can exist, it's just not likely. This doesn't exist. Okay, moving on to our nitrogens. This is a very common way to see nitrogen. 4 different bonds with a positive charge. We're going to explore some chemistry where that nitrogen has a triple bond on one side, single bond on the other with a positive charge. Where it has 2 double bonds on either side. Or, this is the one version that's not drawn up here, or where it has a double bond and 2 single bonds and a positive charge.
That's what that is.
This one here?
No,
Oh.
no, that's totally my fault. I just didn't draw the single bond.
Okay, because this actually would have had this would have a +2 charge.
Yeah.
5 minus 3. Okay, so I'm going to just modify yours then. So if this has a double bond and 2 single bonds, it gets that positive charge. How many lone pairs on these nitrogens? 0. No lone pairs. All right, I only got one option down here. 3 bonds, all in a triple bond to nitrogen. And I can spread that out to be 3 sigma bonds, or I can have a double bond and a single bond. Neutral nitrogen has how many lone pairs? 1. Negatively charged carbon has how many lone pairs? 1. So I want you guys to recognize a pattern as you move across the periodic table. Atoms prefer to have more lone pairs. An atom to the left with the same number of lone pairs would have too many electrons. No one gave me a negatively charged nitrogen. Sad. But the pattern here is remove a bond, add a lone pair. So I can have 2 single bonds and 2 lone pairs with a negative charge, or I can have a double bond and 2 lone pairs with a negative charge. I want you guys still to be thinking about what those hybridizations are too as you go.
No radicals for nitrogen?
Okay, yeah, sorry. There is a nitrogen radical in its neutral state. This is not very common, but it would exist. Thank you.
That's just by shooting light at it?
Who said that?
Well, that's how you make a radical for halogenation.
So yes, you can just shoot light at it and make a radical this way. You don't have to. Sometimes radicals form chemically. All right. On to oxygen. In its positive state, oxygen is going to have a similar bonding environment to nitrogen in its neutral state. So we can replace nitrogen in any of these scenarios with an oxygen and get our answers. I've already got oxygen with a triple bond. The only thing that wasn't shown there, its charge. We have to show charge. But then I could have oxygen with a double bond and a single bond, or oxygen with 3 single bonds. Each of these instances, oxygen only has 1 of its lone pairs, which is why it has that positive charge. Moving down, our 2 most common ways to see oxygen in its neutral state. 2 bonds, 2 lone pairs. These lone pairs look like they're going through a breakup. You can also have oxygen with 2 lone pairs, 1 bond, and 1 radical. Again, a little less common. You maybe saw it in OChem 1 though. In a negatively charged environment, this is a positively charged oxygen. You'll notice that it has the same bonding as this. So this one is not a neutral nitrogen, but it's in the wrong category. This one here, I don't, would be 6 minus 1, 2, 3, 4, 5. So I think this would actually be plus 1. But again, not something you're really going to see, so I'm just going to cross that one out. Similarly here, it's got those 2 bonds, 1 lone pair and 1 radical, so this would be positively charged, but not something you'd expect to see. But here, we've got it. 3 lone pairs. It's only missing what? It's charge. So we'll put a little negative charge next to it. That's what we get. That's what we'll call something oxide. Oxide is O2 minus. Alkoxide is a carbon bonded to O minus. Hydroxide is H bonded to O minus. So that's what we have there.
Oxygen with just a radical, no bonds.
No, we won't look at it.
No.
All right, let's look at our halogens. We've got some diversity of halogens here. You could put X, but it's not a bad idea to just pick one and work with it. Bromine and chlorine are 2 of the most common, so this is great. With positively charged halogens, the most common states that you'll see is 2 sigma bonds, 2 lone pairs. Remember, that's oxygen in its normal bonding environment. When halogens do it, they don't have enough electrons for themselves, positively charged. Or a halogen with a double bond and a positive charge. That's great. Neutral halogens. This might look a little confusing because this is a sigma bond that's being drawn, not a negative charge. Halogens like to have 1 bond, 3 lone pairs. You can also see halogens that have 3 lone pairs and a radical.
That's pretty common, right?
I would say halogens maybe form radicals the most, but those of you taking Ochem 2 lab this semester, I believe you'll be working with something called tempo, and tempo is an oxygen radical, so you will get to use oxygen radicals.
You can store radicals?
Yeah, sometimes.
They don't react with each other or whatever the container is?
It's a good question. I actually don't know. It just got dropped off, so I'll have to check in on that.
Okay.
Negatively charged halogens. The only way to get there is for that halogen to have 4 lone pairs. Great work. How did this exercise feel? Like writing your ABCs? No? I want it to feel like writing your ABCs. So, if this doesn't feel as easy as ABC yet, then at the end of the week, I want you to set a reminder to build the atomic charge table and do it from scratch and see how many of these you can get just off the top of your head. And then a month from now, I want you to set a reminder, build the atomic charge table and see how many of them you can get. Keep doing it until you feel like this comes naturally. I understand that some of you went above and beyond and had some very creative ones. For instance, the halogens can take on a neutral state when they can expand their octet. And they can do that by having many, many multiple bonds. But it's rare that they do, especially in organic chemistry. So I know some of these are just going to take practice and recognition and time spent with the compounds. But see how many you can do from memory until they become really familiar to you. Yeah? Now we have touched on chemical representation already quite a bit, and I want to make sure that we are all in agreement on how we represent molecules. One thing that we're not going to do this semester is use a lot of Lewis dot structure. Takes way too much time, shows a lot of detail, but creates a lot of clutter for our large molecules. We're going to spend a lot of time with bond line structure. And we may see some condensed molecular structure as well. I'm not as big a fan of condensed molecular structure most of the time, but I do see its benefit from time to time, and I really see the benefit in you guys recognizing it. So, Lewis dot structure. You show every bond, lone pair, and atom. So let's take a molecule like alanine. Honestly, you don't need to copy this down if you don't want to, because, like I said, it's too cumbersome. The other thing we always show in Lewis structure is charge as well. You guys know phenyl, or you know alanine? Sorry? It's not just an amino acid. It's the smallest amino acid. All of the other amino acids have this same carbon chain plus more. So that's what I like about alanine. I'm doing the least to draw this. You'll notice that this is neutral because my nitrogen has 3 bonds, 1 lone pair. My oxygens all have 2 bonds, 2 lone pairs. And my carbons all have 4 bonds, no lone pairs. Bond line structure makes some assumptions, and this is where I really want to make sure we're on the same page. We assume carbons at the ends and bends. That I can't take credit for. There was a student that said the end and bend, because I used to say vertexes and end of segments, which was too wordy and hard to spell. So every end and bend in a carbon chain in your little zigzag lines, that's a carbon. Unless it ends at an explicitly shown atom. Now, this is not really one of the rules, but I would encourage you not to mix and match. So don't have carbon chains and then just show one carbon randomly and still try to use all of the other rules. It just gets a little challenging to interpret. We also assume enough hydrogens at each carbon and we're doing one of two things. We're filling the octet or we're matching the charge. So you assume as many hydrogens as you need to get that carbon to an octet, to get it to 4 bonds, or to get it to the charge that it wants, or the charge that it has, excuse me. But we always show heteroatoms. Can you tell me what that means, heteroatoms?
Nitrogen, oxygen, halogens, fluorine.
Good. Organic chemistry is the study of hydrocarbons and its derivatives. Anything that's not a hydrocarbon, nitrogen, oxygen, halogens, etc.
Any metal?
Metals have to be explicitly shown. The only thing you can assume are carbons and hydrogens. You must always show formal charges. And what I mean there is positive or negative. And you may assume lone pairs. That's because there's a lot of lone pairs and they're not always relevant. So one challenging question that I always put on exams, especially on OChem exams, is I will say, look at this structure, how many lone pairs are assumed? And you need to recognize which heteroatoms have how many lone pairs given the charges that are present. So that table is your ABCs. It builds up all of the molecules that we're going to be studying all semester long. So if you can quickly recognize a bonding pattern and the charge that goes with it, or a bonding and charge pattern and the number of lone pairs that go with it, it means you'll be able to read a structure a lot quicker. So let's interpret alanine as bond line. Oh, there's something I realized I didn't put explicitly in our rules, and I want to put it so that we can't have any disagreements about it later. If I would, I'd put it right here with always show, but instead I'm just going to put it as another always show. Always show hydrogens attached to heteroatoms. I think I could have done this better by saying always show heteroatoms, their hydrogens, and always show formal charges. You'll notice that my carboxylic acid explicitly says OH, and my amine explicitly says NH2. I do not just have a line down to nitrogen, and because there's no charge written, assume how many hydrogens and lone pairs must be. Hydrogens on heteroatoms are always explicitly shown. You guys are okay with this? Is there anything about bond line structure you don't like?
I guess I like putting the bends in, so when there's triple bonds, I always forget that I shouldn't have a bend there.
That is a really good point. And you know what? When I looked back at my OChem 2 notes after a while after graduating, we learned alkynes in OChem 2. And I drew my alkynes like that in OChem 2. Now, I will say it's challenging for me to know that you're doing things accurately when you do this because I often miscount it. I've actually pretty cleanly connected my bends to my triple bond, but a lot of students have this like connection, which I read as additional carbons. So someone might try showing a 6-carbon chain, but I count 8 carbons in it, and then I take points because it looks like it's 8. So if I can give you any advice on drawing that linear segment, is just start there and then do your zigzag off of that. It does usually make the zigzags uglier. Yeah. But it's better to have your geometry reflect the structure as best as possible. Or to make it clear to me what's going on. So maybe you have these bends, but you actually show your carbons in them. And maybe that makes it a little bit easier for both of us to interpret. Earlier I said I don't like mixing and matching. And you're assuming all of these carbons, but you're explicitly showing these. I want to clarify a little bit more about what I meant there. I would not like to see a carbon here, where you are explicitly showing the carbon and not assuming it, but you're still assuming it's hydrogens. So if you're going to show a carbon, show me its hydrogens as well. That I'm okay with. But don't assume the hydrogens while showing the carbons. That's where it gets awkward to interpret.
So with your bond line structure, for my previous professor, especially, and of course, like with arrow pushing to get points, or even just to get points on a molecule, we had to show lone pairs. So it would be okay on the exam to end with that and not have the lone pairs?
Correct. In my mechanism problems, I have a list of things that I'm looking for. So I say always show formal charges and relevant lone pairs. Not all lone pairs are relevant to a mechanism. For instance, we'll do a lot of reactions with carboxylic acids this semester. The lone pairs on the OH of the carboxylic acid are almost never relevant. They don't perform anything in the reaction. But one of the two lone pairs on the carbonyl oxygen will be relevant to the chemistry. You don't need to show both because only one of them will be used. So you can just show one lone pair as necessary. If you don't show it and you just show an arrow starting from the atom, you're not using that arrow correctly, and that's what you lose points on. Not just because you didn't show the lone pairs. But in my opinion, if a lone pair is not relevant, you do not have to show it. Now, on the other hand, this didn't feel like ABCs to you guys. So maybe it is best to show all of your lone pairs until it does feel like ABCs. When was the last time you sat down and sang the ABCs for yourself? Right. It gets a little cumbersome and tedious to do it once you know it really well. When was the last time you drew all your lone pairs? Well, if you ask me, never, because it gets a little tedious and cumbersome. I only draw them when they're relevant. And truth be told, I do sing my ABCs a lot because I alphabetize your tests. And I am going through it constantly to make sure I'm alphabetizing correctly. Questions about bond line structure? Do we need to see examples where there are charges?
Why not?
Sure. Let's look at what happens when alanine self charges. So this amine is actually basic at pH values where the carboxylic acid is acidic. So there is a Zwitter ion form of alanine where the carboxylic acid is a carboxylate and the amine is an ammonium group.
Can you get that by tautorizing?
It's not tautomerization.
Could you?
No. It's not
Would
tautomerization.
it just go to the other oxygen then? Nitrogen?
No. No. I mean, I guess that could be tautomerization, but... So tautomerization is... Okay, maybe it is a tautomer. Tautomerization is a catalyzed structural rearrangement. And there is a hydrogen rearranging. And it probably is catalyzed because nothing's being consumed or produced. It's not the context I would want you to think about tautomerization in, though. Right, okay, condensed molecular formula. Yeah?
Do other nitrogen bond line structures? Or
Sure.
are there like nitrogen chains instead of carbon? And you show carbon instead, or just
No, it's not as common for nitrogen to create longer chains with itself. In condensed molecular formula, we're not assuming any of the atoms, but we're assuming some of the bonding character. So let's take alanine and condense it further. We have a CH3 group, which is bonded to a CH group. And that CH group has a group coming off of it. So we might be able to put in parentheses after that CH NH2, or a lot of times condensed molecular formula still has branches being drawn off of it. And then we have a CO2H group. Or sometimes it's written as a COOH group. In the case of some carbonyls, this compound is acetaldehyde. We can abbreviate this as CH3CHO, not COH. OH makes you think of an alcohol, so we write it as CHO, which is to say hydrogen is connected to carbon, oxygen is connected to carbon. And then we get carbonyls like ketones, where we actually put the oxygen in parentheses so as not to confuse it with being an ether. It's not COC, it's CO double bond bonded to C. So these are some common condensed molecular structures. The next one that I want to show you guys would be the benzene. I'm going to move this so we can see it a little bit more. Our benzene ring has 6 carbons with alternating double bonds. And let's make this a ketone as well. There are 2 ways that we can abbreviate the benzene ring. Its true condensed molecular form is C6H5. And then from that, I've got COCH3. This helps us segue into another shorthand in condensed molecular structure. And that's if we use IUPAC abbreviations. We're going to do some review of IUPAC, and we're going to practice IUPAC throughout the semester as well. But I want to give you guys some ideas. Here is 1-bromobutane, written in its condensed molecular form. We can write it as CH3, 2 CH2s, followed by CH2Br. But because it's just a straight butyl chain, we can also write it as BuBr. That would be a condensed molecular form. And if you wanted to emphasize the fact that it's a straight chain, it's a normal chain, you would put NBu to indicate normal, or straight chain unbranched. We can even do this when it's not really necessary, like methyl chloride doesn't have a bond line. Well, it does. It's just a stick. And I know some of you show it. It feels a little awkward. Just a stick going to Cl. But we can abbreviate this as MECl. Or we can look at tert butyl alcohol, which can be written as CH3 3COH in its condensed molecular form. And how could we abbreviate it using an IUPAC abbreviation?
Isobutyl?
Not isobutyl. TBUOH. Lowercase t to indicate tertiary. Oh,
Is that
man.
what TERT stands for? Tertiary?
Yes, sir. We're out of time, and I was just getting to the good stuff. Don't forget that Lewis dot structure, bond line structure, very flawed. it's a very easy way to look at the size and connectivity of a molecule, but it in no way explains the reactivity of a molecule. So when we come back on Thursday, we're going to get into my favorite topic, molecular orbital theory. This view of molecules doesn't give you the size, or it's not easy to show the connection of all of the atoms, but it explains why certain bonds break first. It explains why certain bonds have certain orientations. And it's a really useful transition into resonance. So we're going to go into MO theory. We're going to look at resonance and acidity. And after we get through that, we're going to just get into more of the terminology and IUPAC stuff. So next week, we'll go back to reviewing some more basics. All right? After next week, you have your first unit test. And remember, I have set that up before the drop deadline. I hope all of you can stay this semester. But if you want to know what one of the higher stake assignments feels like for this class, you'll get that unit test before the drop deadline so that you can kind of feel out. All right? Have a great night, guys. I'll see you on Thursday.